Welcome student, how are you? I am D.R MAJHI, teach physics for NEET, main and advanced. Now today I will be discussing the magnetic field due to a circular coil at its center and on the axis of the coil. And I will be solving some numerical related to it. If you are new, please subscribe my channel for my new videos which will be beneficial for you for your NEET, main or advanced preparation. Now let's start. Magnetic field due to current element ideal vector at the center of the circular coil is dB vector is equal to mu naught by 4 pi I dl vector cross r cap divided by r square, where capital R is the radius of the circular coil. Okay. Now the direction of magnetic field at the center is directed normal to the plane of the paper and it is outwardly. So dB equal to, look at this, mu naught by 4 pi I dl vector into 1 into sine 90 degree divided by r square. Look at this. This angle is 90 degree. That is why this is the 90 degree. Therefore, dB equal to mu naught by 4 pi. This is the ideal by r square. Now, mu naught equal to 4 pi into 10 to the power minus 7 Weber per ampere meter is the permeability in the free space. Now, the total magnetic field due to whole circular coil B equals to, look at this, this is the mu naught by 4 pi, this is the I r square and this is the integration of dl from 0 to total length 2 pi r. Therefore, look at this, B equals to mu naught I 2 pi r divided by 4 pi into r square. Therefore, B equal to mu naught I divided by 2r. Therefore, magnetic field at the center of the circular coil is mu naught I by 2r. If the number of turns in the circular coil be capital N, then B becomes mu naught N I divided by 2r. Okay, now a magnetic field at the center of the circular coil of radius r carrying current I is given by B equal to mu naught I by 2r, where number of turns in the coil is 1. Now, if this circular coil of radius r is converted into a smaller coil of n number of turns, then radius becomes, look at this, capital R by n. So, magnetic field of this coil is mu naught n I divided by 2 into smaller. This equals to mu naught n I and this is the 2 into capital R by n. So, this is the mu naught I by 2r into n square. So, this is the n square into B. Therefore, a coil of radius capital R is converted into smaller coil of number of turn capital N, then magnetic field changes to n square times. Okay. Now, magnetic field due to semicircular coil. Look at this, the magnetic field due to semicircular coil B equals to theta divided by 2 pi into mu naught I by 2 r. Now, this angle is theta. Here theta equals to pi. So, B becomes, look at this, pi into 2 pi mu naught I by 2 r. So, B becomes mu naught I divided by 4r. Okay. Now, magnetic field due to quarter circular coil, this angle makes an angle 90 degree, that is pi by 2. So, here B equals to mu naught I by 2 r twice r into theta by 2 pi. Here theta equal to pi by 2. If theta equal to pi by 2, look at this. So this becomes mu naught I divided by 8r. Okay. Look at this. This is the I current flow through a semicircular coil of radius r1 and r2. Look at this. The magnetic field due to this circular coil is directed inwardly, and magnetic field due to this circular coil is outwardly. So net magnetic field at the center of the circular coil is magnetic field produced by smaller coil minus magnetic field produced by larger coil. Okay, so look at this. Here B equals to mu naught I divided by 4r1 minus mu naught I divided by 4r2, and this is directed, look at this, this is directed in inwardly. So this is the mu naught I by 4 into 1 by r1 minus 1 by r2. Okay, please like, share on this video. If you are new, please subscribe my channel for my new videos relating to NEET, main and advanced. Look at this. A circular coil of radius 0.1 meter carrying current 10 ampere. We have to calculate the magnetic field at the center of the circular coil. Now look at this. Here B equal to mu naught I divided by 2r. Now here I equal to 10 ampere, R equals to 0.1. So this is the 4 pi into 10 to the power minus 7, and this is the 10, and this is the 2 into 0.1. So this is the 2 pi into 10 to the power minus 5 Tesla. So this is the 6.28 into 10 to the power minus 5 Tesla. Okay. Look at this. A wire of length 3.14 meter forms a circular coil of radius 0.1 meter. Now we have to calculate the magnetic field at the center of the circular coil if current is 10 ampere. Now look at this. The length of the coil is 3.14 meter. Radius of it is 10 to the power minus 2 meter. Now we have to calculate the number of turn. Now number of turn r into 2 pi r, this equals to 3.14. So look at this. This is the n equal to 3.14 divided by 2 pi into 0. This is the 10 to the power minus 2. Therefore 314 divided by 2 into 3.14. Look at this. This is the 100. So this is the 50. Therefore magnetic field B equals to mu naught Ni divided by 2r. Now what is the mu naught? Mu naught equals to 4 pi into 10 to the power minus 7. Now here N equals to 50, I equals to 10 ampere, and R is 10 to the power minus 2 meter. So you can easily calculate the magnetic field. Now calculate it. What is the magnetic field? So this is the 4 pi into 10 to the power minus 7. This is the 50, and this is the I equals to 10, and this is the 2 into 10 to the power minus 2. Now this cancel out, 2 pi. Okay. So look at this. This is the 100, 5. So this is the pi into 10 to the power minus 2 Tesla. Okay. Now look at this. This is circular coil carrying current I in a anti-clockwise direction. We have to calculate magnetic field at the point P on the axis of the circular coil. The magnetic field at the point P due to current element ideal vector is given by dB vector is equal to mu naught by 4 pi ideal vector cross r cap divided by r square, where r is the distance of P from the ideal vector. Okay. So direction of magnetic field at the point P is normal to the r vector and also normal to the ideal vector. So that is directed along this direction. Okay, now magnetic field due to another current element ideal vector which is diametrically opposite to this is also directed along this direction and same magnitude as that of it and direction along this direction. Okay, so the magnitude of magnetic field dB becomes, look at this, this is the mu naught by 4 pi I dl sine 0 degree, sorry, ideal sine 90 degree divided by r square. Look at this, the angle between ideal vector and r vector, look at this, this is the, look at this ideal vector along this direction and this is the r vector. So this angle is 90 degree. Therefore the magnitude of magnetic field at the point P due to current element ideal vector is I dl divided by r square. Okay, now this magnetic field resolved normal to the axis and along the axis. Now along the axis becomes b sin theta, db sin theta, and normal to the axis is db cos theta. In the same way, this magnetic field also resolved along this direction and along this direction. Now the component normal to the axis of the circular coil becomes 0 and the components along the axis of the solenoid will be added. So total magnetic field on the axis of the solenoid B becomes, look at this, B becomes integration of 0 to 2 pi r, and this is the dB, it is a mu naught by 4 pi I dl by r square and sin theta equal to capital R by R. So look at this, this is the mu naught by 4 pi I into R by R cube integration dl 0 to 2 pi r. Okay, therefore this becomes, now this becomes mu naught by 4 pi, this is the IR into 2 pi r divided by r cube. Okay, therefore B equal to, look at this, B equal to mu naught by 4 pi, this is the I into 2 pi r square by r cube. Now 2 pi r square equal to A. So this is the mu naught by 4 pi, this is the 2ai by r cube, where capital A is the area of the coil. If number of turn in the coil be capital N, then magnetic field B is equal to, look at this, mu naught by 4 pi, this is the 2NAI by r cube. Now 2NAI is called magnetic moment of the coil. So this is the mu naught by 4 pi, this is the 2 capital M by r cube. This is the magnetic field due to circular coil. Okay, from this condition we conclude from this relation we conclude that a current carrying coil behaves as a magnet whose one side behaves as a n-pole and other side behaves as a south pole of magnetic moment M equals to NAI. Now anti-clockwise the current, look at this, anti-clockwise the current represents n pole and clockwise the current represents south pole, and magnetic moment in both case, this is the NAI and M equals to, this is the NAI. Okay, now a numerical. We have to calculate the distance of a point on the axis of the circular coil where magnetic field is 1/8 of magnetic field at center of the circular coil. So look at this, the magnetic field on the axis is 1/8 the magnetic field, 1/8 of magnetic field at the center. Now look at this, the magnetic field on the axis mu naught by 4 pi, this is the 2m by r cube, this is the 1/8 of magnetic field mu naught I by, this is the 2r. Okay, now look at this, this is the mu naught cancel out. Okay, now 1 by 4 pi and this is the 2ai by r cube, and this is the I by 16r. Okay, now look at this and this is the 2. and this is 8 and this is the 2. Okay, now look at this here. Here I cancel out. Now look at this here, 2 here, pi capital R square by pi into R cube equals to 1 by 8 R. So look at this pi cancel out, therefore small r cube equals to capital 8 R cube. So this is the 2R whole cube, therefore small r equals to 2R. Now small r equals to, look at this small r equals to root under of capital R square plus x square. So this is the 2R. Now capital R square plus x square equal to 4R square, therefore x equals to root 3R. Therefore distance of the point from the center is root 3 into R. Look at this is a infinite long straight conductor and this is a circular coil of radius R. This is also infinite long straight conductor and this is circular coil of radius R. Here current flowing in the circular coil in anti-clockwise direction, but here in clockwise direction. We have to calculate the magnetic field at this point and this point. Now magnetic field at this point, look at this, the magnetic field at this point B equals to magnetic field due to straight conductor plus magnetic field due to circular coil. Now look at this, the magnetic field due to straight conductor mu naught I divided by 2 pi R, and this is directed, look at this is directed in this direction, that is this is the outward direction. Now this is the circular coil, this also in the upward direction, so this is the mu naught I by 2R. Therefore look at this, mu naught I by 2 pi R equals to 1 plus pi. This is the magnetic field due to the circular coil, and this is the expression of magnetic field due to circular coil as well as straight conductor. Now in this direction, look at this, the magnetic field due to straight conductor, this is the mu naught I by 2 pi R, and this is direction is outwardly. Due to this circular coil, it is directed in inward direction. Therefore this magnetic field mu naught I by 2R, and this is the cross. Okay, therefore net magnetic field B equals to, look at this, mu naught I by 2 pi R. This is the greater than this, so this is the pi minus 1, and this is the in the inward direction. Okay, next, now look at this is the n-sided regular polygon having perimeter L and carrying current I as shown in figure. Okay, now we have to calculate the magnetic field at its center, and we have also calculated the magnetic field when n tends to infinity. When n tends to infinity, the regular polygon becomes a circle. Look at this is a triangle. Number of triangle is formed here is n. So this angle, look at this angle becomes 2 pi by n. Now a perpendicular drawn from this point to this point. Okay, from this point to this point. So look at this angle, this small angle, this angle theta 1 equal to theta 2 is equal to pi by n. Now look at this distance. Look at this distance is L by 2n. Total length L, number of side n, so each side is L by n and half of it is L by 2n. So look at this length capital R by L by 2n is equal to cot pi by n. So R equals to L by 2n into cot pi by n. Now magnetic field B equals to, look at this is the magnetic field B equals to n into mu naught by 4 pi, this is the I by R into sine theta 1 plus sine theta 2. So look at this, n into mu naught by 4 pi, this is the I by R, and this is the 2 sine, look at this, theta 1 and theta 2 both are same, therefore 2 sine pi by n. Now this is the mu naught n I by 4 pi. Look at this, r equals to L by 2n. So L by 2n, so 2n is in numerator, and this is the cot pi by n, and this is the 2 sin pi by n. Okay, so look at this, this is the 2, this is the 2, so 4. So this is the 4 n square I by 4 pi mu naught, this is the L, and cot pi by n, this is the cos by sine, so this is the sine square pi by n by cos pi by n. Okay, so look at this, this cancel out. Therefore magnetic field B becomes, look at this, n look at this, mu naught n square I sine square pi by n divided by pi L cos pi by n. Okay, pi L cos pi by n. Now we have to calculate the magnetic field B when limit n tends to infinity. Limit n tends to infinity, this is the mu naught n square I sine square pi by n divided by pi L cos pi by n. Okay, let n equals to 1 by y. Therefore when n tends to infinity, therefore y tends to 0. Therefore look at this here, limit y tends to 0, limit y tends to 0. Look at this, this is the mu naught by pi L, mu naught by pi L, and look at this, this is the sine square pi y, sine square pi y divided by y square, divided by, look at this, y square into cos pi y. Now look at this expression, if multiplied here pi square, okay, and this is the pi, look at this is the 1, and this also 1. Okay, therefore the required expression, look at this, B equal to mu I, look at this, mu into I into pi square by pi L. So magnetic field mu naught pi I by L. Now as L is the perimeter, so L becomes 2 pi r. So this is the mu naught pi I by 2 pi r. Therefore this is the mu naught I by 2 r. So this is the expression of magnetic field at the center of a circular coil. Okay, I hope this video will be beneficial for you. Please like, share and comment on this. And don't forget to subscribe my channel to get the new video which will be beneficial for you for your preparation for board, NEET, main and advanced. Okay, thank you.